Here's the solution to homework set number 4 for ECE 320, Electronics 1. Now the first problem is to find the voltages and currents on a min-max circuit. What I like doing is first find the voltages. So starting out, if I just had a blank circuit, I've got these two diodes. One of them is on. If I assume the 3-volt diode is turned on, this will be 3 plus 0.7. I've got 0.7 volts anode to cathode, making this 3.7 volts. That doesn't work because that's more than 0.7. That turns on the first diode, and both diodes can't be on, so that's not true. So diode 2 is off. If diode 1 is on, I get 1 plus 0.7 volts, giving you 1.7 volts right here. Now let's go over on the right-hand side. If diode D is on, this is 9.7 volts. Again, that can't happen. 9.7 turns on this diode. If diode 5 is turned on, I get 7 plus 0.7, 7.7 volts. So now that we have these figured out, take the middle diodes. One of these is turned on. If diode 3 is turned on, I get 1.7 minus 0.7, 1 volt. That doesn't work because I now have 6.7 volts across diode 4, so that doesn't work. If diode 4 is on, I'll have 7.7 minus 0.7, 7 volts. Okay, so that works. Now find the currents. I've got 12 going to 1.7 across 1K, 10.3 milliamps. 12 going to 7.7 over 1K, 4.3 milliamps. And 7 over 10K, 0.7 milliamps. This 0.7 milliamps has to come from somewhere. Let's change the color to red. So this, since only diode 4 is on, this 0.7 milliamps comes from this way. So that's 0.7. The 4.3 milliamps has to go somewhere. 0.7 goes left, so the remainder goes right. That's 3.6 milliamps. 10.3 milliamps has to go somewhere. Diode 3 and 2 are off, so the only choice it has to go through diode 1. So that's 10.3 milliamps. So that's how you solve this first problem, finding the voltages and currents. If I throw it in Circuit Lab, I'll get slightly different answers. Again, for an ideal diode, I get nice round numbers like 0.7. Or 0.7 volts is actually not exactly 0.7. So the current, instead of being 10.3 milliamps, actually is 10.3. Instead of being 0, there's a slight negative current. Again, this is backfed. So there's a very small current going backwards. That's the negative. It's 76 picoamps. So that's 0.0000007 milliamps. Not 0, but pretty darn close, essentially 0. Diodes do conduct going backwards, but the current is really, really small. I4, instead of being 0.7 milliamps, is actually 0.706. I5 is close. Again, when you simulate it, you should get answers that are close to what you calculated. They will be different. Diodes aren't ideal, but they should be close. If you built the circuit, again, I should get very similar answers. So there's Circuit Lab and its answers. Problem 3 is a Clipper circuit. Now with this one, you're given the blue line. Draw a circuit to implement it. So the first step is to draw your straight line approximations. That's the orange lines. And I'll draw an orange line. My requirements say you have to be within half a volt. So I want this distance, when I deviate, to be less than 0.5 volts. As soon as I deviate by more than 0.5 volts, like right here, add a new line. When that deviates by more than 0.5 volts, add a new line. When I'm done, I've got 3 different line segments. These corners are where the Zener diode turns on. So one Zener turns on at 3.8 volts. The second one turns on at 9.5 volts. So when I design my Zener circuit, and I forgot, 3.8, 9.5. So this is a 3.8 volt Zener. This is a 9.5 volt Zener. Okay, next, the slope. Defined, come back, where are you? I lost it. To find R0, that's the initial slope. This is a non-inverting amplifier. The gain is 1 plus R0 over R4. So when I drew this line, the initial slope was 1.93. That's 1 plus the ratio, making R0 933 ohms. That takes care of this part of the curve. Next, the slope turns to 1. What happens is when diode 1 turns on, I suddenly get a voltage divider. This dumps some current, and the gain becomes R1 over R1 plus R3. So the slope is now 1. The slope is your voltage divider times the gain of the op amp. Solving backwards, R1 is 1072 ohms. Next part of the curve. Over here, the slope then drops to 0.4. That's when the second zener turns on. When the second zener turns on, and here think Thevenin, looking left, I see a Thevenin resistance. Thevenin resistances, ignore the voltage sources. I see these two resistors in parallel and a voltage divider. That voltage division times the gain gives you your slope. And the slope should be 0.4. So the slope of 0.4 is your voltage divider. That's R1 in parallel with R2 times the gain of the op amp. Solve, the parallel resistance is 261 ohms. I found from before R1 is 1000 ohms, so R2 must be 345 ohms. So when you're done, here's your circuit. Again, your circuit might differ a little bit, depends upon how you draw your straight lines, but this is the one I got. Should be close, but maybe a little bit different. In Circuit Lab, if I sweep V1, have V1 go between 0 and 10 volts, and plot Vy, this is what happens. V1 goes between 0 and 10 volts, and the output looks like this. This is where the first zener turns on. This is where the second zener turns on. So that's a Clipper circuit. Neat thing about that is I can implement any function as long as it's monotonically increasing, meaning going up, using an op-amp circuit. I'm not exactly sure how this is useful, but you can do it. Today what I would use is just a microprocessor and calculate what you want Y to be. But you don't have to use a microprocessor. You could use diodes. For example, we got to the moon in the 60s. That was before microcontrollers. We were able to do it. We could compute functions using hardware circuits like that. Problem 5 is design a Clipper circuit. And what happens is if this is my input, I want the output, let's do that in blue, to be clipped at 3 volts. So if I go up above 3, I clip, and clips at minus 4 volts. So I want this to be the output. Clips at plus 3 and minus 4. To do that, just use 2 Zener diodes back to back. If this is a 3 volt Zener, it's going to clip at 3 plus 0.7. This is a diode. It still has a 0.7 volt drop across it. So if you want to split hairs, I actually want to make this 2.3 volt Zener. Then I'll clip at 2.3 plus 0.7 plus 3 volts and make this a 3.3 volt Zener. So it clips at 0.7 plus 3, 4 volts with a minus sign, minus 4 volts. And if you check it, apply a sine wave at the input and plot V2. What happens is this one clips at plus 3 and minus 4. And notice it's not a perfectly straight line. Zener diodes are not perfect. They're pretty good, but not perfect. As the current goes up, I get a slightly higher voltage drop across the Zener. But that's problem 5. Problem 6 looks at a transistor. First, label the regions and find beta. Some textbooks call that HFE. Depends upon which textbook you're using. Means the same thing. To find HFE or beta is pick a point, like right here. At that point, when the base current is 5 milliamps, the collector current is 250, 50 times as big. At 40, it's 200, 50 times as big. At 3, it's 150, 50 times as big. So that tells you right there that beta is 50, or HFE, pick your favorite textbook. The regions then. In the active region, IC is beta times IB. The op region, this puppy is a diode. I need 0.7 volts to turn it on. If I don't have 0.7 volts at the base, there's no current. If the base current is 0, the collector current is 0, and you're off. That's this point right here. The x-axis is the op region. And over here, if I have enough voltage from the power supply, that's this guy, if that's big enough, I can produce the current. If my power supply is too small, I no longer produce enough current and I'm saturated. Another way to think about that is a load line. This circuit has a load line. Actually, go on to the next problem. Draw the load line for the circuit. It's 12 volts is the x-intercept. 12 over 50 is 240 milliamps. That's the y-intercept. Between the two, I have a load line. When I increase Vn, I start over here. When Vn equals 0, I am at 0 current, off. As Vn increases, I start moving along the load line. What happens is the base current increases and beta IB goes up. As beta IB goes up, the intersection of the load line and your current IB is your solution. Up until I get to here, I can never go negative. If I go negative, then what happens is that VCE is negative and the transistor is producing energy. That can't happen. So over here is not possible because you can't produce energy. And I can't even quite get to 0. This will be a small voltage drop, close to 0 but not quite. And that's where we assume about 0.2 volts. If I try to go less than 0.2, it'll saturate at about 0.2, ballpark. So that's where it saturates. If I ever have beta IB more than this point, it saturates at 0.2. So that's the third region, saturation, active, and off. Problem 7 is draw the load line and mark where you're operating. At 0 volts, I'm right here. 0 volts produces no current. No current, beta IB is 0. At 3 volts, I've got 3 minus 0.7. Again, this arrow means diode. 0.7 volts drop across the diode. 2.3 volts at 1K is 2.3 milliamps. So here's 2, here's 3, here's 2.3 milliamps. There's my operating point. And at 6 volts, 6 minus 0.7 is 5.3. 5.3 milliamps is up here. That tries to make this the operating point, which can't happen. So instead, I come down here and saturate at 0.2 volts. Or the current can never go above 240. It'll actually saturate about 236 milliamps. And the last problem, if you built this circuit and vary the base resistance, I added a column. I can measure the base voltage, the collector voltage, and calculate IB. If I know Vn, this point, that's 4.3 volts. 4.3 volts across, 5 minus VB over 100 is the current. 5 minus VC over 100 is IC. Take the ratio, I get 1.19. This one I know is saturated because this is close to 0.2 volts. It's trying to go negative, but it can't go below 0. So that's saturated. Add a 1K resistor. Same thing, I measure VB, measure VC, calculate IB, calculate IC, take the ratio. And again, this is close to 0.2, telling me I'm saturated. I'm going to make this a 10K resistor. VC went above 0.2, I'm now active. Active is the voltage is bigger than 0.2, less than 5. Take the ratios, and that's actually my current gain beta. These aren't beta because I'm saturated. I lose gain. I go from this curve down. So if I was on this curve, I would have a gain of 100. When I come down, the gain is less than 100. So when you saturate, the gain is less than beta. So all this tells me is that beta is at least 11. How much more I don't know. Here the gain is at least 1.1. How much more I don't know. At this point when I'm active, I actually know beta. Beta is 98. At 100K, again I know VB, VC. This is again active mode. It's between 0.2 and 5. The ratio of IC to IB is 100. Again, this should be roughly constant. And at infinity, I'm at 5 volts. The current is 0. The gain is 0 over 0, which doesn't tell you anything. This is the off state. So that's problems 8 through 10. And that's homework set number 4 for ECE 320.